Hello everyone, I'm Matteo Mauro. I'm a researcher at the Istituto Nazionale di Fisica Nucleare, and today I'm going to talk about the dark matter interpretation of the Fermi-LAT Galactic center excess. I worked on this paper together with Martin Winkler of Stockholm University. So as you might know, several groups have found an excess of gamma rays looking to the gamma ray data of the Fermi-Large Array Telescope in the direction of the galactic center. The galactic center is a very complicated region because you need to model the data with a galactic interstellar emission model, point sources, isotropic template that accounts for extragalactic sources unresolved by Fermi, the Fermi bubbles, and several groups found that adding also dark matter template, this dark matter template takes a lot of flux, a lot of photons, and it's detected to be very bright and highly significant. Here you see the flux as a function of energy that is peaked at a few GeV, and this excess is spherically symmetric with the shape compatible with the Navarro-Franke-White, and the flux of this excess is compatible with the dark matter signal. So there are other astrophysical interpretations that are possible that have been investigated in the past. For example, cosmic ray protons or leptons injected from the center of the galaxy. But these interpretations cannot be compatible with all the characteristics of the excess. For example, the hadronic scenario is not spherically symmetric, while the leptonic emission is not fully compatible with the flux as a function of energy. Thanks to Bartas et al., Lee et al., and Machas from 2015, all these groups have found some evidences that there is a faint population of pulsars located around the bulge of the galaxy. And so pulsars, and in particular millisecond pulsars can be a possible interpretation for the galactic center excess. But recently, Lin, Chang, Zong, and others found that actually the methods used in these papers in 2015 are not very robust against imperfections of the interstellar emission model to fit the data. And so they casted serious doubts on the pulsar interpretation. And so starting from the recent 2 years, again, the interest on the dark matter interpretations have boosted significantly. So given the current confusion and very exciting debate on the interpretation of the galactic center excess, I started to work on this topic and published 3 papers on the PRD journal. The first 2 as a single authors, where I made the data analysis of Fermi-LAT data, refining and finding more precise data for the characteristics of the galactic center excess. And then in the third paper, I worked together with Martin Winkler on the interpretation of the galactic center excess as dark matter and using a multi-messenger approach. So in the second paper for the characteristics of the galactic center excess, I used the most recent data set of Fermi. I used also some techniques to minimize the imperfections of the interstellar emission model and the newest templates for the galactic foreground. And so the characteristic I find are the following. For the flux is peaked at a few GeV. With the low and high energy tail, I'm able to detect the galactic center excess up to almost 100 GeV. The galactic center excess is centered around the dynamical center of the Milky Way. And the most important addition of my paper is the study of the morphology as a function of energy. So since the morphology is compatible with the Navarro-Franke-White shape with a slope roughly of 1.2, 1.3, I decided to fit this Navarro-Franke-White slope in different energy bins. So I performed the analysis between basically 500 MeV up to 30 GeV, finding that the slope parameterized with gamma of the Navarro-Franke-White is basically flat with energy. There is no energy dependence. This has remarkable consequences for the interpretation because dark matter is expected to have no evolution with energy for the spatial morphology, while, for example, cosmic ray electrons would have a slope that is energy dependent. And finally, the excess is basically spherically symmetric. So all these characteristics are very compatible with the dark matter signal. And so this motivates us to try to find a dark matter interpretation for this galactic center excess. This is what we have done in the paper 3 together with Martin, where we have done the first comprehensive and fully consistent analysis of dark matter for the galactic center excess and also for other targets like dwarf-spheroidal galaxies, still in gamma rays and in Fermi-LAT data, but also using the most promising cosmic rays, namely positrons and antiprotons, to see if the dark matter interpretation of the galactic center excess is compatible for gamma rays, cosmic rays, in particular positrons and antiprotons. And this is the first fully consistent analysis because we are using the same dark matter density profiles, the same propagation models for all the analysis we have done for this paper. The first thing we have to calibrate is the dark matter density, and we use together the spatial morphology of the galactic center excess that we find in the second paper, and also the rotation curve data from the latest paper of Salas et al. 2019. So the galactic center excess is going to calibrate the density in the inner few kiloparsec, while the rotation curve data beyond a few kiloparsec. So the dark matter density is parameterized with the geometrical factor J, and we use 3 different values of the local dark matter density between 0.3 and 0.4, basically. And finding 3 benchmark models, mean, med, and max, that minimize, average, and maximize the J factor that varies from the mean and max by a factor of 7 from basically 100 up to 700. So we are going to show the results for the mean, med, max model because these 3 models bracket pretty well the uncertainty for the dark matter density in the Milky Way. So the first thing we do is the easiest thing. So we fit the galactic center excess flux in gamma rays with a single channel. So dark matter annihilating into couples of leptons, quarks, antiquarks, or gauge bosons. Gauge bosons, in particular W, X, the X boson, and gluons, no, gluons is okay, but the X boson, W, and Z, they are too massive to contribute to the galactic center excess. So the only gauge bosons considered is the gluon part. And leptons and quarks can provide a pretty good fit to the data. And here you see the summary of the results for the annihilation cross-section and dark matter mass. For example, the Borton anti-Borton quark channel fits with a dark matter mass between 40 and 50 GeV and the cross-section between 1 and 2, 10 to the minus 26 centimeter cube per second. The fit is very good for the peak, but it misses the high energy tail. So we can try to complicate the model with the 2-channel case, so dark matter annihilating with the branching ratio in one channel, Y minus branching ratio in the another channel. The channels that improve the most the fit are the plus or minus baby bar, mu plus mu minus baby bar, with a mass between 30 and 50 GeV, cross-section close to the thermal one. And here you see the coupling parameters for the branching ratio. And these fits are able to basically be consistent with the data also at the high energy tail, with an improvement in the fits up to 8 and 9 sigma significance. So since we find that the galactic center excess can be fitted very well with the 2-channel case, we can try to find dark matter also in dwarf-spheroidal galaxies that are very dense astrophysical objects for dark matter. We use the latest sample of Payson Strigger in 2018 with 48 dwarfs, but we try other samples finding similar results. So we make a combined analysis of gamma rays from dwarf-spheroidal galaxies, but we don't find any significant signal, and so we put upper limits for the annihilation cross-section as a function of dark matter mass. Here you see the upper limits with these red, blue, and black curves compared to the best fit from the galactic center excess with the green data point, and the green band is for the mean, med, and max model. So you can see that the upper limits from the dwarfs are not ruling out the galactic center excess fit with the green band. So basically dwarfs, the non-detection from the dwarfs of gamma rays is still compatible with the dark matter interpretation of the galactic center excess. And for the first time, we test this also for the 2-channel case in dwarf-spheroidal galaxies. Antiprotons have been used in the past to constrain very tightly dark matter, and they are also very interesting because several groups have found an excess in the antiproton data of AMS roughly at 10 GeV, and this has been associated with a possible dark matter signal. And so we make a combined fit to the proton Voyager AMS data, anti-proton data from AMS and Pamela, and to the AMS Bohr over carbon ratio. And the best fit for delta and the normalization of the diffusion coefficient are reported here. And we fixed the size of the diffusive halo L to 4 kiloparsec, but we also test other values for L. This is the best fit we have with simply astrophysical model. So with no dark matter, the fit is very, 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 very good. If we add dark matter with the best fit found with the bottom anti-bottom channel, there is a worsening of delta chi square of 44 that is associated to the 6 sigma worsening. And this is the result for 3 kiloparsec. And the worsening can be clearly seen here in the anti-proton fit, but also for the Bohr over carbon ratio. So since we don't find any significance for the dark matter contribution in anti-proton data, we can put upper limits for the annihilation cross-section as a function of dark matter mass. But the upper limits are really very, they depend very much on the value of the size of the diffusive halo. Here, for example, we see the upper limits for the bottom anti-bottom part for L that changes from 1.5, 2, 3, and 4 kiloparsec. So the upper limits decreases with the larger value of L because antiprotons can survive more in the diffusive halo, and so the flux of antiprotons from dark matter increases. And so we are able to constrain, for example, the purely hadronic channel, for example, bottom anti-bottom quarks to be compatible with the upper limits if L is smaller than 1.7 kiloparsec, while the semi-hadronic channels, for example, the E plus E minus, BB bar, or charm quarks are compatible with the upper limits of antiprotons for L smaller than 2.5, 2.6 kiloparsec. The muon channel is a completely unconstrained because they don't produce antiprotons. So basically, these antiprotons are very good channel to constrain purely hadronic or semi-hadronic channels. These upper limits for L are in tension with, for example, the analysis of radioactive nuclei made by Giannolini et al. And with observations of gamma ray and radio observations that points towards value of L larger than 2-3 kiloparsec. Positrons have been used in the past also to find constraints for dark matter going into leptons. The low energy part is basically produced by secondaries, while the high energy part is probably due to pulsar wind nebulae. Since the contribution of pulsar wind nebulae is not very well known, we use two scenarios, a conservative approach where positrons are given only by secondary production, and an optimistic approach where the positrons are fitted with an analytic function. So we find upper limits for the cross-section. In the conservative approach, the upper limits are compatible with the best fit to the galactic center access, while in the optimistic scenario, we are able only to rule out dark matter going purely in E plus E minus or going into E plus E minus and with some other contribution from hadrons. So to conclude, we have found that the characteristics of the galactic center excess are compatible with dark matter annihilating particles. We try to find gamma rays also from dwarf-stellar galaxies that have a very low astrophysical background and are very dense of dark matter, but finding no signal. And so we put up limits for annihilation cross-section that are compatible with the galactic center excess signal as given by dark matter. Antiprotons, they don't produce any signal for dark matter, and the upper limits can constrain the purely hadronic or semi-hadronic channel, while positrons constrain the dark matter going into E plus E minus or E plus E minus and some other channel. So the candidates that survive are dark matter annihilating into mu plus mu minus with a mass of 60 GeV and the cross-section close to the thermal one, or dark matter going into mu plus mu minus, a plus or minus, and BB bar with a mass roughly 40, 50 GeV and the cross-section close to the thermal one. Now we have to study more the pulsar interpretation in the future, refine interstellar emission models to try to have more power to constrain our dark matter interpretation. So thank you very much and bye-bye.